first session is, as you know, the first workshop is going to be about timers and GPIOs, and we'll start from the base down, and we'll see it all in a very practical way. So from an application point of view. So first of all, the workshop is structured as follows. We'll build an application towards the end of each workshop, right? So the first workshop, we are going to build an IR remote, like just like the projector remote, which has various buttons on it. We are just going to mimic that remote, but only the power button. So by the end of the workshop, using your microcontroller, you should be able to switch off the projector, each one of you. That is the goal. So in order to do that, what we have to do is understand a few concepts. And in IR, there are majorly two concepts, that is timer and GPIO only, right? So I'll first explain to you how IR works. It'll be a very quick introduction and a few protocols that are followed in IR, and then I'll hand over the session to Shashank. Okay, so here is a basic block diagram of what we are going to do. There's going to be a push button, which will act as your power button, which will communicate with the 1343, which will trigger an IR LED, and which will send the code to the projector. Okay, so how IR works? Basically, IR always sends bits to the projector or to the receiver. Okay, so it's a stream of ones and zeros. And how this is sent is, there's an IR LED in each remote and a receiver, right? But the problem is, the IR LED emits IR rays, and IR rays are all around us. Like, we generate IR, we radiate IR because we have heat in us, right? So any body which is heat has IR as well. So how does the receiver know which is the particular code, like which is the code to be received and which is to be ignored, because we are surrounded with IR. Right now, the projector is not responding to any of the IR that is present around it. It will only respond to the remote. How does this happen? We do something known as modulation. Okay. Now what happens is, the IR LED is flickered at a high rate, usually 38 kilohertz or 36 kilohertz. So the IR which is there, the LED switches on, switches off, switches on, switches off at a very high frequency. Okay, and when this happens, the receiver is tuned to that particular frequency. So in our case, it is usually 36 or 38 kilohertz in case of all commercial remotes. So whenever it receives a 36 or 38 kilohertz modulated IR wave, only then it responds. Now I'll tell you how it works. Okay, so we have to do a certain type of modulation, right? And there are various methods of doing it. There is pulse position encoding, pulse distance encoding, pulse width encoding, Manchester encoding, and Fsk modulation. What this means is that to transmit a 1, in case of pulse position encoding, for example, to transmit a 1, the IR LED is flickered at 38 kilohertz for some time, and that time is defined according to the protocol, which we'll look at next. So it is flickered for some time, and then nothing is done for some time. So whenever there is flickering IR LED, that is a 1, and when nothing is done, that is a 0. This is pulse position encoding. So based on where the pulse is, you tell that, okay, 1 or 0, based on the position of the pulse, right? Pulse distance encoding, what this means is, the LED is flickered for some time, for a fixed time, and then nothing is done for some variable time. Okay, so suppose the LED is flickered for say 2 milliseconds. I'm just giving an example. The LED is not flickered for 2 milliseconds, but say it is flickered for 2 milliseconds and nothing is done for 5 milliseconds. So 2 and 5, whenever the receiver receives a 2 millisecond pulse and nothing for the next 5 milliseconds, it takes it as a 0. Okay, and whenever it receives a 2 millisecond pulse and say nothing for the next 10 milliseconds, it takes it as a 1. This is pulse distance, because you are here you are changing the distance of doing nothing. You are not changing the width of the pulse, right? You are not doing anything for a variable number of time to convey that whether it is a 1 or a 0. But in pulse width encoding, it is the exact opposite. As the name suggests, the width of the pulse is varied. So here I send a 1, like I modulate it for say 2 milliseconds and do nothing for 3 milliseconds, that is a 1. I modulate it for 5 milliseconds and do nothing for 2 milliseconds again, that is a 0. So this is pulse width, where the width of the pulse is changed continuously. And a Manchester encoding, this is a popular encoding method. What is done is, you do nothing for the first, say for the first 5 milliseconds, and then modulate for the next 5 milliseconds. So nothing, modulation, this is a 0. You modulate first, do nothing for the next 5 milliseconds, this is a 1. So based on where the pulse is, like is there pulse at the beginning or is there pulse towards the next half, determines whether it's a 1 or a 0. And Fsk modulation is a very impractical method. What this does is, suppose it is modulated at 38 kilohertz for first 5 milliseconds, and then it is modulated at a higher rate for the next 5 milliseconds. So whichever is modulated at 38 kilohertz is taken as a 1, and whichever is modulated at a higher frequency is taken as 0. Obviously, you can see that we need to do modulation twice, and this requires more hardware. The receiver has to be able to receive both frequencies. So because of that, FSK is very seldom used. But these 4 are pretty common. And the most common among them is Manchester encoding and pulse width. Pulse distance also, but not that much. So IR protocol. Basically, you can divide a protocol into 4 separate units. You start with the start bit. The start bit lets the receiver know that, okay, something is coming. You have to receive the next set of commands or whatever I sent. And next, the address bits. Now, address bits is usually 8 bits in length. Okay. So suppose Philips, for example, the company, they have certain protocol defined. So for them, the address 1 might be the projector, the address 2 might be the TV, address 3 might be the VCR player, the DVD player, whatever. So if there are 8 bits, you can have 2 raised to 8 addresses, right? 256 addresses. So totally 256 addresses, and then followed by command bits. So each device can have 8 command bits. You understand how it works? So the projector can have 256 commands. The TV can have 256 commands. That's how it works. So this is a different combination of address and command bits to talk to a particular receiver. And then the stop bits. The stop bits lets the receiver know that, okay, the code has sent, the code is done, like there's nothing more to come, right? And the stop bits are usually, you don't send anything for a specific time. So you don't send anything for 2.6 milliseconds. That lets the receiver know, okay, that I'm not going to receive anything more, like the code has been received fully. Okay, now let me talk about NEC protocol. This protocol is followed by LG, like my TV at home follows NEC protocol. So what it does is, first, this is the start bit I was talking about, 9 milliseconds plus 4.5 milliseconds. So continuous, it sends this pulse initially. Then my TV knows, okay, something is going to come, I have to receive this now. And then comes the address bit followed by the not of address bit, right? 8 bits of address followed by not of address. This in turn is a verification sort of a step, because if we receive this, then we have to receive the not of this. This makes sure that, okay, the address is correctly received. Same thing with the command and then the command bar. There is no stop bit in case of NEC, but usually after this there is a cool off period. Like usually you don't send anything for the next the next coming time immediately. So this is how the NEC protocol works. And a logic 1 is 560 microseconds of modulation, as you can see, and the rest is nothing. So whenever the receiver receives this, it is a 1, okay? And whenever the receiver receives this, it is a 0. So can anyone tell me, is this pulse width encoding, pulse distance, what is this? Pulse distance. Pulse distance, right? Because the width of the pulse is same. This is pulse distance encoding. And with NEC, there is something called as an extended NEC protocol. As you can tell, since there are only 8 bits for address, I can only access 256 devices with this. But in some cases, you might require to have more addresses. So this is extended to 16 bits as well. So that gives you 2 raised to 16 devices that you can control. But command remains 8 bits itself. Now next, I'll talk about RC6 protocol. This is by Philips. And this is one of the most well-defined protocols, you can say, and majorly in use these days. So the protocol goes like this. First, there is a leader symbol. The LS stands for leader symbol. So you send a 1 here. And what this does is, based on how well it is received, the receiver is able to calibrate itself to the oncoming signal, to the incoming signal, right? So the leader symbol is just for that. And then comes the start bit. The start bit is always a 1. This is again to let the receiver know that something is going to arrive, like you're going to get a command. And then the TR, that is just the time, like some time which is given for it to receive, so that it can calibrate well. That is some cool off period in between, okay? And then I'll tell you about the mode bits, yeah. So these are 3 bits, 0, 1, and 2. Usually it is a mode 0, that is all 3 bits are 0. And what all 3 bits are 0 means is that I'm letting the receiver know that the control bits, that is the addresses, are only 8 bits. And the information is 8 bits. If I change this, if I have a mode 001, that lets the receiver know that the address is not 8, the address is 7 bits. And the control is 9 bits. Do you get it? So these mode bits decide where the split happens. Is it a 8-8 split? Is it a 9-7 split? Is it a 6 and 12? 6 and 12, what am I saying? Yeah. that split. So this is how the mode bit defines where the split happens, but usually it is 0, 0, 0 itself, right? So 0, 0, 0 means 8 and 8 split. You understand this, right? Okay. What? TR is just a time which is given for the receiver to receive something. Like when the mode ends, TR is a cool-off sort of a period. So in that period, like it lets the receiver know that the address bit is coming now after some time. So just to calibrate that. Okay, and then there's a signal free time of 2.6 milliseconds. So you can't have 2 button presses within 2.6 milliseconds. You have to give at least 2.66 milliseconds between 2 button presses. And this is the leader symbol. Right, it's 2.666 millisecond of pulse and 889 microseconds of nothing. Right? And then this is the logic 0, logic 1. Which encoding is this? Manchester encoding, right? And then the trailer bits are as follows. 889, this is the logic 0, this is the logic 1 of trailer bits. Okay? It's pretty self-explanatory. Just you can go through it once. Okay, so where do the concepts of timers and GPIOs come in this? It's very obvious. See, now we are dealing with 444 microseconds, 889 microseconds of time. And this is very crucial because even if you miss by say 10 or 15 microseconds, the receiver is going to reject the code. You have to be very accurate here. And hence, you require timers. Okay, I'll tell you exactly how timers come into picture. But like usually what we write is we write software delays, right? We pass a function, we run a while loop till that count, and that is not as accurate as this. It can't get also, you can't get 889 microseconds with that. So to generate this, first I have to have a timer which switches off, switches on, switches off, switches on my GPIO for a very specific time period. So if I want to transmit 38 kilohertz, say 38 kilohertz of time period, so that's going to be 1 by 38 kilohertz time. Right, 1 by 38,000, and it's going to be off and on in that time. Half of the time is on, half of the time is off. So you're dealing with 1 by 72,000 seconds. 1/72nd thousand of a second it has to be off and it has to be on. So that crucial time periods you're dealing with to modulate it at 36 kilohertz. Right. So in that case, you have to have a timer which runs for that much time, and during that time the GPIO is off. As soon as that much time is over and when the GPIO is supposed to be on, it hits an interrupt. In that interrupt, you switch on the GPIO. Again, that time passes, you switch off the GPIO, so on. And you have to do it for how much? 889 microseconds. So you see 2 timers come into picture here. One timer which is modulating it at 1 by 72,000 seconds, and the other one which makes sure that the modulation happens for 899 or 889 microseconds. Understood? So this is the importance, and obviously GPIO, because it has to switch on, switch off, switch on, switch off, right? So we'll be doing that in the ISR, and that is what the workshop is about. We are going to be doing this by the end of the workshop. Okay? Okay, so that's my presentation. Thank you for listening. I'll hand over the stage to Shashank now. Thank you.